In this video we will study the atom, or the lighter atoms in this case, and we will go into greater details. So the forces within an atom is purely electromagnetic. So if you want to understand this video, you should look at the earlier videos on electromagnetics. So you have to know electrostatic, magnetism, and electromagnetic induction. It's essential for the understanding of the following. So we will start off from a classical orbit. There is no understanding why it doesn't work with the classical orbit. It just seems that the establishment say that this cannot be classical, so they invent a lot of strange things to try to make something out of the atom. So we start off from this. We say we have a very heavy nucleus in the center, and we have some electron, one electron going around. Then classically this electron should be on the equator, let's say, and it has the perfect circle if the nucleus is heavy. Okay, so we start out from this. Now we have then that the electron feels the electric field from the nucleus, and if he gets some speed he will circle around, so it looks very nice. But from the DAON theory we know that when the electron feel an electric field from the external part, he will start to rotate around an axis parallel to the field that he feels. So if you go to an atom, he has a movement around this central nucleus, and at the same time he feels the radial electric field from the nucleus. So he will have also a rotation around an axis parallel to this electric field. But if he goes around like this, and then he has a rotation at the same time like this or like this, then he will be deviated. He will move out from the equator. He will move up or down, depending on which direction he goes. And this is the reason why you cannot have a classical orbit. It doesn't work because of the magnetic field, which is a rotation of the electron. This is quite simple. Now, earlier we have already looked at, from induction, we know that this rotational velocity of the electron divided by c corresponds to the electric field at the same position, which you can express in this manner here. That's the reference radius of the electron divided by the distance in square. It's equal to the order, which is the velocity of rotation divided by c. So you get this. Now this you can of course use to make some calculation of the force, transverse force, which is pushing this electron up or down. And you have this expression here. So you have that a force that is deviating the electron from its classical orbit. It's moving up or down, and since this force which are deviating the electron is perpendicular to the electric field and to the velocity of the electron around the nucleus, it means that this force will not change the energy of the electron. It just will push the electron on its potential surface to a smaller radius. And this can be up or down depending on, from the direction, the handedness of the trajectory. If it's right-handed, it will go up. If it's left-handed, then it will go down. Okay. And this is then we should take out something else also. It is we know also that the direction of the rotational axis of the electron is important, because it gives a force in the direction of the rotational axis, which is not necessarily the direction of velocity. So you can have, as you see in this figure, you can have a rotational axis which is not parallel with velocity. This is like the Earth going around the Sun. I mean, the axis of the Earth is inclined. It's not straight in any sense. It's up, and it's when you go around the Sun, and you have the axes which are moving relative to the Sun. but it's always in the same stable direction, and it's going around the sun. So this is the axis can be completely in a different direction then you could be perpendicular or to direction of the velocity, but it could also have any other direction. So in the case of the atom, this is also true. And you have another thing also in the atom. It is that, for instance, the moon, when it goes around the Earth, it has always the same side that you can see from the Earth. You don't see the back side of the moon because it follows exactly the rotation around the Earth. And this is due to gravitational forces. In the case of the atom, the electromagnetic force is much stronger than the gravitational force. So the rotational axis is always fixed relative to the nucleus. It stays in its position, it's going around like this, and it's always in the same direction as you see in this figure here. But as I told you before, the rotational axis has an inherent force in the direction of its axis, and when this is not aligned with the velocity, then you have also a transverse force given by the rotational axis. This is expressed in this formula here. So the angle eta is the angle between the angular momentum vector, that is the electron goes around axis, the angular momentum vector goes like this, and then in the trajectory around you have the electric field like this and the angular momentum like this. So this is the angle between these two vectors. It's the eta. So next question to ask is, so why doesn't the electron find a stable orbit just a bit outside the classical one? Well, the problem then becomes slightly different, and this comes from another video which we have seen just before, and this is the associated wave of the electron. When you have a closed orbit like the electron has within the atom, then the associated wave must have some sort of resonance. You cannot have any angle or any phase of the wave where you go around, because then the electrons should start to move around and be very unstable. So this is not possible. The electron has to find some sort of resonance to obtain the stable orbit of the inside the atom. So this can be done in various ways, but usually you should go to the first, you have to have one complete orbit or one half complete orbit, and not 1/3, 1/4 is highly unlikely. You have to make a lot of turns to get into a stable orbit. But if you have one half spiral in one orbit, then you can just make two orbits and you have a closed resonance. So this is a possibility. So you can then have, we can then write up some formulas. You see here that sinus for this eta, what I told you about earlier, should be equal to the number of spiral on the orbit of the electron, divided by the number of orbit if it was a classical, so if you stayed on the equator, let's say. This is due to the potential level where you are. If the potential doesn't change because the energy doesn't change, which means that if you slide up on the potential surface, you reduce the radius, but you keep, let's say, the energy associated with the potential level. So if you look at this, you can then obtain some quite simple ideal relation characteristics. So you have the radius, the speed, and the angular momentum, as you see here, where the 0 indicates the value of the lowest energy level for hydrogen atom, and theta is the effective charge seen by the electron. This is ideal because in reality the electron doesn't see really the center of or the direction of the external electric field. It's not in the central position of the nucleus, but it can be very well be on the side. So and then this gives that the effective charge is different and the direction of field is different, etc. So this is just in the ideal case. It can be first line of direction, let's say, is an idea of what the values of this electron could be. So what you could have now is first we should say that to specify this associated wave, this is if you have an integer associated wave, so you have one turn and you have an integer spiral, 1, 2, 3, whatever, then you have a problem from stability, because if you see this is moving around this electron, and it also has an associated wave, it's moving like this, and then you find that if you have integer angular momentum, let's say, then the minima of the electron closest position towards the nucleus is repeating. That is to say, in the turn you always come back to a minus in the same minimum in the same position and the maximum on the other side. This is very bad because it makes some oscillation, tuck, 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 it's increase, and it becomes unstable, and it's not possible usually. This is a quite well-known phenomenon in the, for example, cyclotron accelerator side. You can see that this is a serious problem. But if you have half integers, that is 1/2 spiral for one turn of the electron, for instance, or 3/2, 5/2, etc., etc., then you get that the minimum distance from the nucleus becomes the maximum one turn later, which means that you have an exchange between minimum and maximum at the same position, and this allows the electron to be much more stable. So usually you should have these half integers, which gives a much better stabilization. Even it could be even stable, not even instability, but really stable. So this is what you could expect. So if you look at this, then you have that half integral, so you should have some, to see here, the g, that is the angular momentum, times the reduced Planck's constant of Planck. Could be 1/2, 3/2, 5/2, that is really stability criteria, which normally is okay. And integer is bad. I mean, you have instabilities associated with integer, which is, makes that this is not possible. Of course, when you have this possibility, then the electron can jump from one energy level to the other, but it has to find the correct angle between the angular momentum and the orbit, and also the distance, the radial distance, giving the correct angular, the spiraling number of spirals has to be coincide. So you have very specific values or characteristic of the electron. So this is the jump between different levels is due to this fact. An electron by itself, when it moves in space, he has a rotation around himself, which is left-handed, going in this direction. Left-handed, like it. Okay, so, but if you look to the trajectory around the nucleus, this can be right-handed or left-handed, no problem. The same thing about the spiraling movement of the electron. It could be like this, but it could also be like this. So it could be in any direction. No? They are both allowed. You should also know something else. Of course, we didn't say maybe, but if you look to the reference radius of the electron, it's around 10 to minus 15 meter, and you look to the size of the electron, or let's say, no, the size of the atom, sorry. So you have that the electrons are quite far away from the nucleus compared with the electron radius. As we said already when we examined the equations of electric and potential fields, this formula works only at a certain distance from the charge. And in the atom, in fact, if you look to the distance, they are very far compared to the electron reference radius, which means that the atom is purely electromagnetic. There is no other force acting within the electron, purely electromagnetic. So that's why you have to understand electromagnetics before you understand anything about the atom. Okay, so then if you look to the variation of the electric field, I mean, if you use, you can look at this figure here. You see that if you look to the plane of the electron, let's say perpendicular to the angular momentum vector, then the interaction between the electric field of the nucleus and the varying spiraling form of the electron trajectory, in fact this can be almost neglected. You reduce somewhat the interaction, force of interaction, but very small. It's associated with the fine structure constant. So this is quite small, and you can normally you can even neglect it. As we see, it's not so easy to make any strong calculation. So this is almost neglectable for the changes of the energy, let's say. Which is a bit more important is the transverse direction that is parallel to the angular momentum vector. In this direction you have that the force is varying quite strongly, and so that the shape of the spiraling trajectory changes. Not a circle, but it's more elliptical, and but it doesn't influence the energy of the electron. But you should know it in any case that this is not a perfect circle. It's really an ellipse, standing ellipse a bit. And well, okay. And you have this small influence on the energy from the variation of the field associated with the spiraling trajectory. So this, in fact, doesn't look very complicated. Huh? Once you've understood how things are working, it doesn't sound very difficult. So that was at least my reaction. So I made a simulation program, which I call Atomall, and I tried to see what happened. So I put in electromagnetic, the force of deviation, and the associated wave to see what should come out. And the following we will have a closer look at what this gives for lighter atoms. So we will start off with hydrogen. Of course, you can almost directly from what I already said, say that the hydrogen atom is the electron going around the proton is displaced, so that the radius of the trajectory becomes half of what the classical value is. You see this in the figure here. So if you have half the radius, then you have half of the angular momentum, so you get immediately the hydrogen atoms, you have the angular momentum is just 1/2, so you spin up 1/2, it comes out immediately. Okay, so in the closed orbit of the hydrogen, you have a very nice interaction. You have the proton is not standing still, it's much heavier, so he has no associated wave, but he responds to the position and characteristics of the electron, so he has the same type of rotational trajectory. It's also rotating, but he doesn't oscillate as an electron. So, okay, so you get this image here. You see the small point on the side. This is a nucleus, and you have the electron, which is with this spiraling trajectory, which in the perspective looks like this. And with this I obtain the same value as experimental one, 13.6 electron volts. You have the other speed, angle, and radius you can obtain from this table here. So the n is a principal level number, and then you have sublevels, number of turns within the sublevel, the speed, and eta is the angle, as I told you before, and E is the total energy of the atom. This maybe you should be more precise about that. The energy indicated in the tables is the total energy of the potential energy of the atom. It's not possible to make the difference directly in a simulation, or you can, but it's very complicated, because for each atom, if you take away one electron, then the electronic configuration changes completely, and you have to remake the whole calculation again. And this makes that you have after the first atom, okay, this is quite easy, but when you have many electrons, then you have problems. You have to make a sum of all the electrons, energy of all the electrons, and then make the difference between two different configurations to obtain the difference in energy levels of an atom. This becomes quite complicated since the values become high, and the difference for the exiting photon is quite small, so you get quite big error bars. And in fact, you can get some reasonable energies in the first couple of atoms, and then afterwards the error bar becomes so big that it's you cannot even present them. So it's so I don't even present them, I think, in any of this, because it's the difference. Error bar is too big and it's not interesting. The interesting here is to show it, how the atoms are working and how you can place the electron in the round to have a stable configuration, and this should be quite correct. So according to my view, maybe this video on atoms is maybe the most important of the DAON theory, because it can be used in a series of scientific areas like chemistry, medicine, biology, physics, electronics, everything. So this is very important, but the program I made is not working very well because it's quite complicated. So it has to be taken up and maybe redone. We will come back to this point later when first I'll show you the results, and then we will discuss this maybe at the end of the presentation. Okay, so we will continue now with helium. Helium, as we know, it is 2 electrons around the nucleus, and this now this time you see the figure here. Then these 2 electrons must have the same handedness, that is the circle they make relative to the radius of nucleus must be the same for both electrons, otherwise they get instability. This is due to the fact that if you have opposite handedness, then the 2 electrons find themselves in opposite one to the other and turning in the same sense. But then if you have a very slight difference between the 2 electrons, then one electron will go versus inside and the other one will go outside, and this will go be stronger for while time pass, so that you have one electron going away and the other electron going versus inside. So this is a saddle point, let's say, it's unstable and it doesn't work at all. So this is why you have a difference between how do you call them, parahelium and octohelium. This is due to that the electrons has the same handedness or the opposite handedness. If they have opposite handedness, then this is unstable, and one electron will go up to the next energy level when it becomes stable. So this is typical for when you have helium type atoms. They all behave in the same manner. It's not possible to have the same opposite handedness in the same level. Has to have the same handedness. If you have the same handedness, you see that one will be put in a magnetic field, for instance, you will have one up going for it, let's say in this direction, and the other one will be below and go in the opposite direction, and this is stable. Because when they go in the opposite direction, one versus the other like this, then you don't have any slip. There is no saddle point. They just see each other shortly and then puff, piff, puff, puff. They get some kick of the electromagnetic field, but it's continues to be always the same, and this is can become stable. So this is so this means that the handedness is the same for both electrons. If you see then relative to the radius of the nucleus, you have one like this and one under like this. So they have opposite direction if they have the same handedness. Okay. You have also another thing, and this is when you have 2 electrons in the same energy level, then also the spiraling of the trajectory of the 2 electrons should be in the opposite direction. And not only, they should also have 180 degrees phase difference, because in this case, specific case, you have that the 2 electrons, when they are possibly close one to the other, then the distance between them in the movement of the spiral will be constant. So you have some stabilizing action of the two electrons like this. And also when they are far away, it's the same thing. You have they are the same distance between them, which is weaker, of course, but still the same. So this is some sort of stabilizing action, which it's very good. If you have even numbers of electrons, then you always have this stabilizing action between them, supplementary to the resonance condition of the spiral. So this should be noticed. Okay, so now we leave the helium. Of course, you see the values in the tableau. It's about the same as reasonable results. Or if you have some per mil difference in energy, it's not so bad. Okay, what you should say also here is that if you look to the kinetic energy and the potential energy of the electrons, then the difference is very, very small. The difference in these two is just connected to the nucleus movement. So the binding energy you find in fact in the nucleus. The nucleus potential of the nucleus is almost all the binding energy of the electrons. It's all, you find everything into the nucleus. So the electron themselves has very little change of energy, potential or kinetic. So if you make the sum of energy, it's very small. It becomes bigger, of course, for heavier atoms, but compared to the absolute values of the nucleus, these are very small values. This is interesting. I mean, the electron is really keep more or less its energy and kinetic and potential energy, and it's the nucleus who have all the potential energy, or almost. Okay, now we move on to the lithium. Lithium, we try to put a third electron into the K shell, but of course this doesn't work. You get immediately high instability, and this ends up with one electron being thrown out. So this is not possible. So we took one electron a step further ahead, and this is you move it up one step in the absolute value. That is to say, you move the radius outwards, but you reduce the radius of the orbit of the electron with a factor of 2. So you have the angle. It's now sinus for the angle becomes 1/4. Earlier it was 1/2. Now it's 1/4. So that the angular momentum remains 1/2. Okay, so you get further away, but you have shorter radius, so the angular momentum becomes 1/2 reduced Planck constant. Okay, so you get this picture here. You see these values, and you have the table which indicates this. I've written this now in degrees because it's the angle in degrees. We are more used to that instead of pi or whatever. And as you see, the value of the energy now becomes has an error bar which starts to grow, and you get into problems one step at a time. Each atom you add another electron, you get into more and more difficulties. Just for to say, for instance, for the lithium, very simple in principle, but you have that there is no resonance between the internal angular velocity, angular momentum, let's say, and external electrons' angular velocity. Or there's no, it's not an integral number of resolution of the inner electron compared to the outer. There is different, which means that the outer electron in each turn he feels the electric field from the internal electrons in different ways, so it's never repeated. You have always a different trajectory, so you cannot make any precise calculation of trajectories anymore because it doesn't work. You have to look at the mean value of the trajectory and position and everything, because this is you don't have a repetitive movement. You had a repetitive movement for the helium and the hydrogen because they have a simple symmetry, but now with the resonance, different resonance from the two levels, Now it becomes an intermediate value, so you cannot anymore have a precise calculation. So this makes things more and more difficult also for this reason. Well, okay. You have also the fact that the external electron is pushing a bit on the internal electrons. So the electrons is not anymore exactly aligned with each other. They are pushed away a bit, so the angle between them are changed by about 5 degrees. So it's okay. So we come up to the beryllium. So now we have 4 electrons. Again, we have an even pair of electrons, 2 in each energy level. So you can have a stabilizing effect due to the phase shift between the 2 electrons. So this is quite good, stable atoms. Not much to say about this. I mean, you see the values start to become a bit bigger error bound, but it's still quite okay. Okay, so we go on to the boron, which now we have 5 electrons. So this is a bit more complicated. You can, because now you go from the S to the P sublevel of the atom. This means that the 2 electrons from the beryllium in S state of the S state see each other and are aligned in phase and everything like this. And then if you try to put a third one inside there, it doesn't work, it's unstable. So you have to go out from that. But also I found that the boron, the last electron, has to change direction again. So we have 2 electrons in the S state, which is in certain have the handedness relative to the nucleus, which is, let's say, right-handedness. Then the S level under is in the opposite direction. The handedness relative to the nucleus is in the opposite direction, and the p electron then in the outer part is then again changing direction, so that the P state, P level or sublevel, it has the same handedness as the S state of the K level that is below. And you have here one of the reason, or the reason, for why you don't have a selection rule of G equal 1/2, or it has to be integral. It has to move from one and jump one level to the other one, because otherwise you have opposite handedness. So this doesn't work. So you have to go from one level of handedness, let's say right-handedness, to another sublevel, which is also right-handedness. Otherwise, you get from that you get into a sublevel which has an opposite handedness, and we already seen that this is unstable, so it doesn't work. So that is why you have the delta G equals 1, because you have to jump one sublevel to go to a correct one and on. So you have beryllium, then you have the S level has 2 electrons, and slightly above you have the P level, which is just slightly a bit lower energy, and also it's in the opposite direction, so they don't mix, let's say. It's separated and they stay separated, but they still have some sort of electrostatic symmetry, let's say. So they are, it is stable but not very stable, let's say. It's not very good. The next is much better, carbon. The carbon has 6 electrons. So it's an even pair, and you have a very nice pair, as you can see in the figure. You don't really see very well, maybe, but this is nice and stable. And this is pairs which are clocked in phase, etc. So this is rather stable, nice, no problem. And you see the values written here. It is not very good, let's say. It could be better. But the error bars, I told you, start to grow. So this is we start to get into trouble. Now nitrogen. We move on to the nitrogen. Here you have 5 external electrons. You have 3 in the P shell and 2 in the S shell. And this is less stable because you have 3 in the outer shell, which means that you cannot have the phase is not locked as in the pair. even when you have even electrons, it can lock. But if you have a triangle, then you can make the phase 120 degrees difference, for instance. But I'm not sure that is very efficient. In any case, it works. But so this locking of phase is probably not very strong, but still it has some use. So this is okay. So you see the values here. Then here you have you start to get into more and more trouble of the energy levels. It becomes more and more complicated. So let's move on to oxygen. Oxygen, again, you have an even number of electrons. So this is locked very nicely, and the locking phase is quite stable, like the carbon, more or less. I mean, the oxygen is also a very stable, nice atom. And you see the results is always, I don't have not even indicate the error bar because it's it's not very nice. Now the next one is interesting, fluorine. The fluorine, you have now 5 external electrons. So not only is it not locked in phase, but it's also not stable. I mean, it's not symmetric. You cannot find a symmetric structure for 5 electrons. In a shell, it's really very bad. I mean, they are moving around the electrons. It's very unstable. So here you have an atom which really has an electronic configuration which is extremely bad, which I think it's has to give as a result that this fluorine must have very strange chemical reactions. I mean, it must be very strong, because if he sees some other atom beside him, he will jump on it and make something, or get rid of an electron, or take an electron. I mean, it's this electronic configuration of fluorine is a disaster, and he has to do something about it. So I think this chemical reaction must be very strong for this fluorine. To compare to the others, I mean, the others has a very stable and calm configuration, but fluorine, that's another pound of much. Okay, now we come up to the neon. Neon is, as you know, is a noble gas, because you are filled up the whole, you cannot put more electrons than 6 in this p shell, out of p shell. And I've not tried to come higher than p, because you get really into serious problems. Calculations are long. It's very difficult to find some initial condition which doesn't end up in disaster, and you cannot make a high number of turns, because you get into instability. When you have many bodies of charges to try to calculate this with a ray tracing method, this is not possible. Just some of the lighter atoms that I will show you, I've showed you here, but I cannot make a lot of turns, because this then goes into instability. And of course the energy has a big error bar, and it's not very useful as it is. Okay, so of course then the neon, since it's a perfectly symmetric, you have a connection also with phase locking, etc. And you can make a very nice atom of this. You should also, we can point out here also that since atoms or the electrons are on a potential surface, if you put a magnetic field on a potential surface, you align the trajectory of each electron with the magnetic field as well as possible. But if you increase the magnetic field, then this electron can move on the surface of the potential, and so you get some interesting effect, the so-called Paschen-Bach effect, that is the electrons are moving on the potential surface of the atoms. Okay, so now we come to the comments on the atomol program. I call it atomol, this program, stimulation program of the atom. So this, as I already told you, it is a quite straightforward ray tracing program with some specific conditions of resonance, etc. We use all equations that you have found earlier from electromagnetism. But this, as I told you, this is a very difficult program to do in this way. You cannot take into account the spiraling trajectory, because you don't know exactly the position of the mean trajectory, so you don't know which is the radius or the velocity, etc. So you get into trouble if you try to be too precise. It's not possible, and you have to have some damping mechanism, so it's not jumping away too quick, etc., etc. It's a lot of problem. The initial condition is very sensitive, etc. Not very good. So I think this program should be made differently. It should be made with some fixed structure, let's say circle, for instance, of the electrons, and you should position them. You should calculate the mean effect on these circles and place them more or less in correct position and distance from the nucleus, etc. And then on top of that, you can calculate the mean electromagnetic interaction within this ring, and then you can modify this mean trajectory, let's say, to take into account the mean effects from the electromagnetic interaction. Once you have done that, then you can take this and add the spiral ring movement of the electron, where you now have a fixed mean trajectory, so you can calculate the radius of the spiral, and in this way you can have a stable configuration. You can, when you add the spiral, of course it will change some value of the electromagnetic field, so you have to correct the mean trajectory slowly with time, and but in this way you can stay stable, and maybe you will have less precision of some calculations of energy, etc. But at least the electron will stay put, and you can, as well as possible, calculate energies and position, etc. So this is, I think, the best solution. So you can use perturbation method, whatever you can imagine, to try to keep this in a stable configuration. So this is future works, which I myself is getting old and slow, so I suggest that when people start to be interested in DAON theory, that they take this program and try to develop something nice with it. I think with the help of AI to look for initial conditions, etc., this should be absolutely possible to do. And if it works nicely, this could be an instrument of very important values for research in general in many areas. So this is a very important point. Okay, before we finish this video, we will make some comments on angular momentum and magnetic momentum, because it seems to be of interest, because you can make very precise calculations. Seems to be both, I'm not very sure of the calculation, but you have experimental measurements which gives very precise values. That angular momentum is 1/2 of the reduced Planck constant, and so you get the constant of Planck without any problem, the half. Okay. Anomalous magnetic momentum you get when you get and put a magnetic field on top of the electron. So this is more delicate. You have to introduce then the force-formed magnetic field, which you can do. I will not be too long because it's quite a mathematical play. It's not very easy to develop this in a video, so I will leave this more or less to the people who are buying my book. This is a book which you can find if you just Google it. You say the DAON Theory book, and you will get some information where you can find this book, and if you're interested of the mathematics. In any case, from this you can extract the G factor as 2, and I've made a quick look on higher order, and if you take into account the movement of the electron in the spiral ring movement, then you get a correction factor, so you get I get 2.00232, which is the correct numbers. After that, I'm not sure that I get, because then you have effects of higher terms. If this is one high term, then you have another one, etc., etc. So this is the first 6 numbers are correct, and then I've not tried to go higher than this. So this is could be interesting for somebody who likes mathematics, can play around with that and see if it's correct for 10 numbers, 10 digits. Okay, so this is all for atomic physics. Okay, we will stop here, and the next piece will be a detailed explanation of the photon and the neutrino before we will attack particles. Okay.